Right. We talked about the ear last time. We're going to approach the lecture very much like we did the eye. I'm going to go through the pathway using a visual of the eye, and then I'll go back and go over the notes that I've written on the slides. But as I did last time, I'll keep repeating what I've said before, so it'll be easier for you to take notes. Housekeeping terms, wavelengths. These are measured in nanometers, which is a billionth of a meter. Humans can detect wavelengths between 380 and 760 nanometers. This is called the visual spectrum because it has to fall between 380 and 760 for us to be able to see it. Okay? Light waves are referred to by amplitude, which is, again, the strength, intensity, or brightness. Saturation is the purity of the color, the trueness of the color, and it depends on whether it's radiant light or reflected light. Radiant light is from a direct source like the sun, a flame, something like that. Reflected light is where the waves bounce off of something and then reflect back. But some of that energy will be absorbed. If all the energy is absorbed, the image will appear black. If none of the energy is absorbed, it'll appear white. All right. This be the eye. The light wave comes in and enters first by crossing through the cornea. The cornea is a translucent membrane that covers the eye. Then it's going to go into what's called the anterior chamber. So that light wave is going to go through the cornea into the anterior chamber, and that anterior chamber is filled with a jelly-like fluid, which is called aqueous humor. Okay? So the light comes in, passes through the cornea, passes through the anterior chamber, which has this aqueous humor. Now, the aqueous humor actually is exchanged over time. And so you can injure your cornea and lose the aqueous humor and still maintain your eyesight. And so that's pretty good to know. We pass through the cornea, pass through the anterior chamber, pass through the aqueous humor, and then there is a hole that either enlarges or constricts that's called the pupil. It will regulate how much light gets into the eye. So, light comes in, passes through the cornea, passes through the anterior chamber, passes through the aqueous humor, it passes through the hole that is called the pupil. Okay? Pupil is surrounded by a colored membrane called the iris. That's what gives our eyes its color. Okay? So then it's going to go through the lens. Okay? Now the lens has some very strong muscles attached to it that are called ciliary muscles. These will either lengthen or shorten the lens, which facilitates focusing. The light comes in, goes through the cornea, goes through the anterior chamber, goes through the aqueous humor, goes through the pupil. Now it's going to pass through the lens. After passing through the lens, it's going to go into what we would call the main eyeball. This is filled with, this is also called the posterior chamber. Okay? Now the vitreous fluid that is in the posterior chamber, it gives the shape to the eyeball. And if you lose the vitreous humor, there is a very, very good chance that you could lose your eyesight. The vitreous humor is not replaced. The aqueous humor is. Now, something else I was going to tell you. Oh, the aqueous humor and the vitreous humor has two functions. They help to give shape to the structure that they are occupying, and they also furnish nourishment. So, you've got the light, it passes through the cornea, through the anterior chamber, through the aqueous humor, through the pupil, through the lens, into the posterior chamber, passing through the vitreous humor, and it's going to go to the back of the eyeball, which is called the retina. There are three different layers of visual cells in the back of the eye. Okay? Now we'll start reading a little bit of the notes that I have written for you. The light will enter through the cornea, passing through the anterior chamber, passing through the aqueous humor, passing through the pupil. It goes through the lens. The ciliary muscles will change the shape of the eye. This changing of the shape so it can focus is called accommodation. The posterior chamber, filled with vitreous humor, it too is a jelly-like substance. Now the light will pass to the back of the eye and it'll hit the retina. There are three layers of visual cells, the first being the rods and the cones. There are approximately 100 to 120 to 125 million rods per eye. These are slender, they're cylindrical, and the rods do not detect color. Then you also have the cones. The cones are more fat and stocky. They will release an inhibitory chemical. There are approximately 6 to 7 million cones per eye, and they do detect color. Now, I'm going to tell you, for years and years and years, I had a hard time keeping it straight. Do rods detect color, or do cones detect color? And I was, struggling to constantly remember it, and all of a sudden it came up to me. Color begins with CO, and so do cones. Now that's the way I keep them straight. After that, I never had another problem. Color and cones both start out with the first two letters. I connected them, and so I never had another problem after that. I find little quirky things to try and remember things. All right, so now the light is going to pass through the rods and the cones. There's going to be a release of an inhibitory chemical. Oh, there's a picture of rods and cones. The green are the rods. The blue are the cones. As you can see, the rods are more cylindrical. There's more of them. The cones are stopped here. They're narrow, they're broader. Okay. Next, we're going to go through the bipolar cell layer. Now, before anybody even thinks about it, this has nothing to do with bipolar disorder. Okay? I've had that question many times. It's a great question. But it has nothing to do with bipolar disorder, the mental disorder. All right? These bipolar cells fire. Now, when they fire, they cause the ganglionic cells to react. Now, these ganglionic cells, they come together and their axons will form the optic nerve. So the axons of the ganglionic cells, they come together and form the optic nerve. So, we have the light, it goes through the cornea, through the anterior chamber, through the aqueous humor, through the pupil, then it goes through the lens, it passes through the vitreous humor in the posterior chamber, goes to the retina, and the retina has 3 layers of visual cells, the first being the rods and cones, the second being the bipolar cells, and these bipolar cells fire, and when they do, they cause the ganglionic cells to have a reaction. Now this reaction will travel down each cell axon. Those axons come together and form the optic nerve. Now the optic nerve from the right eye will come together with the optic nerve of the left eye at what's called the optic chiasm. From there, it's going to go to the thalamus, and from there into the occipital lobes. Now, there is a crossover of the image, and I want you to read, let's see here. At the optic chiasm, the fibers carrying the information about the right side of the visual field across over to the left side of the brain, okay? Beyond the optic chiasm, the fibers will synapse in the lateral geniculate nucleus. From there, the fibers will go to the visual cortex located in the occipital lobe. There are 2 color theories that we need to talk about. One's called the trichromatic theory. The trichromatic theory was originated in 1802 by Thomas Young. Now, I want you to think about this as we talk for a minute. In 1802, Thomas Jefferson was negotiating the Louisiana Purchase. Our nation wasn't even really 25 years old. And a guy is sitting there saying, I wonder why we see color. He comes up with a theory, and in 1852, Hermann Helmholtz took that theory and revised it. And Helmholtz says there are 3 types of cones. One type detected red, another detected the color blue, and the third detected the color green. To detect a different color, combinations had to work together, okay? This theory went on for over 100 years until technology could catch up with the human mind. In the 1960s, they were able to prove the trichromatic theory with one exception. Instead of the colors being red, blue, and green, the colors that the cones detect are actually blue, violet, green, and yellow-green. And so we get to seeing colors by different combinations that occur. Then we have what's called the opponent process theory. In 1872, over 100 years ago, he said cones occur in pairs. And as one activates, the other one is inhibited. And so it's kind of like this. He said they occur in pairs, red, green, blue, yellow, and black and white. Now, I have no training whatsoever in ophthalmology. But in my little mind, I've kind of thought about how could one be activated as the other one is inhibited. And I kind of thought about a stick shift. Because as you go down on the accelerator, you're activating the accelerator as you're coming off of the clutch. And so you have this type of movement. As one is completely activated, the other one's completely deactivated. And the opposite. In the 1960s, technology caught up with the human mind. Again, the theory was verified, except, again, for one thing here. And that's that the cells, these visual cells, are not cones. They actually occur in the bipolar layer and in the thalamus. And so instead of these being visual cells that would normally we would think about being in the retina, they're in the bipolar layer and in the thalamus. Well, then we're going to go to the sense of smell, olfaction. If a person is not able to detect odors, this is called anosmia. It can be permanent, it can be temporary. If you have a head cold, you have a sinus infection, and you're all congested, chances are you're not going to be able to smell anything. That would be an example of a temporary condition, okay? Now, as you get older, these cells do not replicate like they used to. And so, as you get older, your sense of smell will not be as acute as when you were younger. Sometimes it gets almost where you can't smell anything. That would be a permanent condition. I had a friend of mine that had a brain tumor, and the brain tumor was right where it affected her sense of smell. She couldn't smell a thing. And when the brain tumor was removed, she was just in awe of odors. And, wow, this is incredible, And so, could have been permanent. That one was restored.
Also, without smell, you can't taste as well as alcohol.
Perfect, because that's what we're going to cover next.
Oh.
Besides the fact that it has to do with the sense of taste, what else? I mean, we've been talking about vision and hearing. I mean, now those are important. Besides the sense of taste, why else would we need the sense of olfaction, the sense of smell? Well, let me see here. If you all started smelling smoke, would that alert you to something?
Yep.
You'd start wondering, is there danger? Now, I've told you all that my husband and I, we don't cook at home. Our friends know if they come over and get coffee, we have coffee, and they go into our refrigerator and they want milk, they better darn well smell that milk before they put it in their coffee. Because, I mean, if they're lucky, it might smell sour. If they're not, it might come out in clumps. I mean, you know, we need the sense of smell to detect danger, okay? So taste and danger. The humans can recognize at least 10,000 odors. Now, I went to a veterinarian. In fact, I went to several veterinarians, and I asked them, how much greater is the sense of smell for dogs than humans? And I got several answers, and they varied from 400 times to 1,400 times. And my thought was, maybe one of the vets was thinking like a bloodhound, which would be 1,400 times, and maybe one of them was thinking like a chihuahua, and that would be like 400 times. But whatever, when you have 400 to 1,400 times greater than humans, if you're grilling on that charcoal grill, and he's whining and begging and such, if you think that hamburger smells good, multiply it by 1,400 times. And that might be why they're putting up such a fuss. It also explains how a male dog can tell a female dog's in heat 2 miles away. Pheromones, absolutely. Well, we are going to go through the olfactory pathway, basically like we did the other two. Now, when you smell something, it's going to go into the nose. The nose, the reason we have a nose, the job of the nose is to collect and filter air. That's it. So when you take a big breath in your nose, it's just to try and filter out particles and to collect the air so it can go into the nasal cavity. The nasal cavity is where the receptors are located. Okay? So you've got these olfactory receptors that are in the nasal cavity. You've taken this breath in, it's gone through the nose, it's in the nasal cavity, and this air has molecules in it that are odor, okay? Those molecules are running around and they're searching, seeking, and finding receptor sites. And they're locking into those receptor sites. When that happens, the receptor will depolarize. Now the message is going to go down the axon. The axons are going to come together and form the olfactory nerve. And do you remember I told you that there was one sense that did not go through the thalamus? It is the olfactory pathways. It's the sense of smell. And so here it goes through the amygdala instead of the thalamus, and then eventually winds up in the cerebral cortex. Now, to smell something, the easier it is to smell, the molecules have to be freer. Now, if I took a bottle of bleach or vinegar or even Lysol and opened it up, it wouldn't take very long at all for the back row to smell it. And they'd be able to identify it. That's because those molecules mix with the air very well and they diffuse very easily. On the other hand, if I said, would you please tell me what your desk smells like? He'd probably have to get his nose down there and sniff, and he probably still couldn't tell me because those molecules are not free. They're not mixing with the air easily. It has to mix with the air easily for us to perceive the odors. Okay? Any questions so far? Let's see, I just went over that. There are approximately 10 million nasal receptors. Each receptor has 6 to 12 hair-like projections called cilia. The lifespan of a nasal receptor is 5 to 8 weeks. There may be as many as 100 receptor sites. The sense of taste. For you to be able to taste something, it has to be in liquid form. Now, what I mean by that is you've probably taken biology and maybe A&P, and they say that the digestion starts in the mouth, and it does. As you are chewing the food, saliva is interjected, and as you're chewing, it becomes more and more liquefied, and it forms a bolus of mass, and then it goes ahead and starts on its journey to the digestive system. But as that saliva is released and your food is becoming more liquefied, the molecules of the food are being released. Okay? They are searching, seeking, and finding receptor sites and locking into them. All right? Secure. That receptor site now, the receptor depolarizes, the neuron fires. The axons of the neurons come together. Okay? They form the gustatory nerve. The message now goes down to the medulla, the thalamus, and then the somatosensory cortex. Once you start getting the idea of the molecules seeking, searching, finding, and locking in, and then the polarization, the firing of the neuron, it's basically the same process on these senses. It's just where they end up, whether it's somatosensory or in the temporal lobes, and the exact receptor site you're looking at. Like in the eyes, the receptors are they're the cell layers, okay? In the ears, it's the hair cells. So, the food has to be in a solution. It has to become emulsified and liquefied. The molecules then will be released. They will seek a receptor site. The receptor site is found. The molecules fit and lock into that site. The site depolarizes. The neurons that are synapsed with it, they will fire. That message then will go down that neuron, down the axon. The axons come together and form the gustatory nerve. The message then goes to the medulla, then the thalamus, and the somatosensory cortex. There are 4 primary tastes: sweet, sour, bitter, and salty. Taste receptors are going to be located in the taste buds. Now, I've always heard them called lie bumps. When you get a bump on your tongue and it's real sore, and you know, oh, what is this? You know, and like I said, everywhere I've always gone, they've always called those lie bumps. Well, those aren't lie bumps. Those are inflamed taste buds. Okay? And they usually heal pretty quick. Each taste bud has approximately 20 taste receptors. Taste buds line the tongue, the roof of the mouth, the back of the throat, and inside the cheeks. Cheeks above the head, above the neck. Life expectancy of a taste receptor is about 10 to 14 days. The maximum amount of receptors that we will ever have is 10,000. And that's when you're a child. As you get older, you'll be losing the ability to reproduce them at the rate that you were as a child. Now, I had an absolutely brilliant question from one of my students several years ago, and it made so much sense. I had never thought about it, but it made so much sense. I just thought, this is absolutely brilliant. He said, you have children that don't like vegetables like broccoli, spinach, cabbage, some of these vegetables like that. And he said, do you think that it's because they have so many taste receptors that the pure taste, they're getting the full amount of the taste, and it's overwhelming to them because as we've gotten older, we've lost some of those, and it's not quite as powerful to us. And I thought, that makes a lot of sense to me. And so, I don't know if that's true, but it sure is a good theory. Sense of touch, all I'm going to do is tell you there's 3 types of receptors on this. Basically the same thing. The mechanoreceptors are a type of receptor that it will detect touch and pressure. Thermoreceptors detect temperature. Nociceptors detect pain. Now, where I'm not going to talk about the touch pathway, I am going to talk about a thing called the gateway theory. Gate control theory, of pain. Now, when some kind of trauma or something happens where pain occurs, those pain impulses are going to be transferred or transmitted from the receptors to the spinal cord. The spinal cord then will release a chemical that they call substance P. Substance P now causes neurons in the spinal cord to send the message to the brain for processing and the perception of the pain. We say then that substance P has opened the pain gate. The brain now perceives the pain, and the neurons that descend from the brain will release endorphins. What are endorphins? They are nature's morphine. They will lessen the pain, lessen the tension, improve the mood. Also, endorphins block the release of more substance P, the further release of substance P. So now we say the pain gate is closed. Now, when I was in grad school, I had to do an internship at one of the psychiatric hospitals. Now, just for the record, psychiatric hospitals do not have emergency rooms. And as I came off of one of my shifts, I was fumbling through the keys, and I wasn't really paying attention to where I was going, and there was a pothole in between my car and the car next to me, and I fell in that pothole like a ton of bricks. I don't know if y'all have ever had an occasion where something happened to you where you didn't know if you wanted to vomit or pass out, but that was the amount of pain that I was going through at the time. I think the bottom of my earlobe was the only thing that wasn't hurting. Everything in my body was hurting. It was too painful to move anything. My hand, my fingers, anything. And I'm just sitting there writhing in pain. Well, I can tell you, my body was releasing a lot of substance P. Okay? Well, I lay there for a couple of minutes and I saw one of the nursing assistants come out, and I knew that it being 5 o'clock, 5:30, that if I didn't get his attention, I was probably going to be laying there all night between those two cars. With everything that I had, I raised my arm, just, help, help, you know, and I was so happy that he saw that, and he comes running over to see what he could do. Now, as a point of information, it is not comforting to a patient when the first words out of your mouth is, I don't like the way your ankle is hanging. That was not comforting. And he said, I'm not going to try and lift you and take you back in. I'm going to go get a wheelchair and bring you back. In the 2.5 years that he was gone to find that wheelchair, I am just laying as a crumpled mass of flesh. He helps me get into the wheelchair. He wheels me into the unit that I was interning in, and the nurse sees my ankle, and it was already very swollen. And she goes, oh my gosh, look at that, what happened? She goes, oh my goodness, this is terrible. We need to do something. What do we need to do? And I said, ice. Ice would be really, really good right now. Well, we don't have ice packs. I don't know what to do. Well, I can't go out and get an ice pack. We don't have an emergency room. And I said, you know, just get some ice out of the refrigerator, put it in a towel, you know, put it on my ankle. Oh yeah, that's a good idea, yeah. We'll just get some ice out of the refrigerator, yeah. She gets the ice, puts it on the ankle, and she goes, no, you know, we don't have an emergency room. I'm not sure what we can do. We don't even have a doctor here. I don't, you know. And I said, if you get me the phone, I'll call a friend, they'll take me to the emergency room. That's a good idea, let me go get the phone, yeah. So she gets the phone. I call my friend, he said, I'll be there in just a few minutes. And so I hang up, and she said, oh, that is looking bad. And she said, you know, that's gonna be really, really hard for you to get in and out of the car and be transported. And I said, I know we don't have splints here. I said, I used to be an EMT instructor. Let me tell you to get some certain things, and we can make a splint. Okay, that sounds like a good idea. And I said, you know, the first thing is we need some magazines. Let me think, where am I going to find some magazines, you know? And, you know, we went through this. And the reason I'm telling you this is because think about that. 15 minutes before her getting excited about not having any splints, not knowing what to do about the ice and such, I was a crumpled mass of flesh that felt like I was in so much pain I couldn't even raise my arm to ask for help. And yet now I'm sitting there saying, please get me some ice, please get me a phone. I'm thinking about what needs to be done, about ready to teach her how to make a provisional splint. I submit to you that those endorphins were flowing. They had shut the pain gate so there wasn't more substance P being released, but there was still pain. I'm not telling you that it got rid of all pain, because it sure didn't, you know. It hurt, I'm telling you. But the endorphins helped to be able to handle the pain. And they blocked any more substance P, so the pain was not as intensified. We have what's called the vestibular sense. It provides information about the body's orientation and movement. It's located in the inner ear. The vestibular sense, there's two parts to it. One's located in the semicircular canals, and the other is in the utricle. Now, the semicircular canals, if you remember that the cochlea looked like a snail, the semicircular canals would have been those antennae. Right here. Okay? Now, the utricle and the semicircular canals, they are all filled with a jelly-like fluid. Okay? Now, the vestibular sense is a sensory system in the inner ear that registers the orientation of the head. Now, so if you turn like that, what happens, there are hair cells in those semicircular canals, and they will move with your head, and at that point, they will send a message to the brain, and your brain now knows what position your head is in. It also has a lot to do with balance. Now, if you have ever had vertigo, you know how an inner ear infection can really mess up your balance. Vertigo is like having a bed spin after you've been drunk, and yet you haven't been drinking anything. It just starts. And if you can't get it under control real quick, you normally get very sick and throw up. Now, the utricle is also filled with a jelly-like fluid. It also responds to movement where the fluid causes the projections to depolarize and send the information to the brain. The brain then detects a change in gravity. So if you were going to start falling and you were about ready to lose your balance, your utricle would help you try and regain that balance. The kinesthetic sense, that is a system of receptors located in the joints that provides information about the location of the extremities. Can you imagine how frustrating it would be if we did not have anything to send the brain information about what our arms and legs are doing? Because we have that information. I mean, you can drive a car, you can do a stick shift, you can bat a ball or play golf, throw a frisbee, dance. All those things we don't even think about, and yet every movement of your extremity, everything is sent, that information is sent to the brain. And we're finished with the sensation chapter. I told you we'd be moving faster. Perception. Okay. There are some housekeeping terms. The absolute threshold is the minimum amount of stimulus energy that's detected 50% of the time. What that means, let's say you have a room that is totally dark, no light whatsoever. You have a light bulb in there, and they are very, very gradually putting enough electricity to gradually turn that light on, and the very second that you start determining any light, then what they do is they do that over and over again, and when they figure out, after repeat tests, the minimum amount of the electricity that it would take for you to detect the light 50% of the time, that's your absolute threshold. It can be any sense, okay? Now, there are studies that they have done for humans, absolute threshold. Some of these things blow my mind. The absolute threshold for vision, they say that 50% of the time, humans can detect a flickering flame like a candle in total darkness 28 miles away. That would be almost like a Lear Conway. Now, you're sitting there and you're saying, no way. But think about our soldiers in the desert. And it gets pitch black on the desert. And if you light a cigarette, that's all it takes for the enemy to know where you're at. And that little bitty flame can be detected miles and miles and miles. All it takes is a little bitty light. Now, in World War II, they used to have what's called civil defense drills. And when these sirens would go off, they would have to go in, cardboard off all of their windows, and nobody in the entire city was supposed to smoke. Do what?
I just have to turn off all the lights.
Yeah. Everything was supposed to be black. No light whatsoever, because the planes above, all it took was just a little minute light, and they'd know where to start bombing. And so, you know, you sit there and say 28 miles away, wow, I don't know about that. When I put it into a different context, and even like in space, you know, space, total darkness, and think about how far they can see and see a little bitty light. So it's not beyond my comprehension or my understanding that the absolute threshold for vision would be 28 miles. The absolute threshold for smell is, I'm thinking it's 3 drops of perfume in a 6-room house. Now, you're thinking, I don't believe that. But let's change it again and say 3 drops of pine salt. Pure pine salt. That's a little bit more believable, isn't it? 3 teaspoons of sugar in a gallon of water. But the tests have been done. 50% of the time that can be detected. Taste, that's taste there. Hearing, they say that you can, you know, one of these watches that still has the second hand, that you can detect the second hand, or you can detect a clock ticking 6 feet away. That one is believable, pretty easily to believe. And the last one is the sense of touch, that you can feel the wings of a fly dropped from 1 centimeter onto your cheek. To me, that's easy. That's easy. And so, the minimum amount of stimulus energy that can be detected 50% of the time, not 100%, just 50. Pattern perception, this is the ability to discriminate among different figures and shapes. Would you please tell me where the circle is?
Or,
The circle, just tell me where it's at.
it's like,
All right. Where's the triangle?
bottom right,
You're right?
no,
Oh,
right.
yeah, all right. Well, look at that. The ability to discriminate among different figures and shapes. Then we've got what's called the feature analysis theory, and that says the theory of pattern perception, stating that we perceive basic elements of an object and then assemble them mentally to create the complete object. What did I just draw? Do what?
It almost looks like a house.
Okay, a house. What do you think it looks like? A house? Okay, what do you think it looks like? A house? What about you?
House.
Straight,
Do what?
that shape, I mean,
What kind of shape?
triangle,
Okay, anything else? What kind of object does it look like to you?
home,
Oh, a house. House.
How many would have said something else if she didn't say house first? What would you have said?
oh, no,
Oh, okay.
I would say the same thing.
Well, you know something? Y'all are all right. You're correct. But, I tell you what else it could be. It could be a crayon. It could have been a rocket. It could have been a pencil. And, you know, even as I'm saying that, you're looking at it and you're mentally assembling pieces and saying, well, you know, okay, maybe that could be a crayon. And if I did this, wow, it's a crayon. But, see, you didn't really need that because your mind visually already assembled it when I said a crayon. And I had somebody looking at me askance with a sconce whip when I said a rocket, all right? Okay? And yes, I could have made that a house. Somebody once said it looked like the Lincoln Memorial. Not the Lincoln Memorial, the Washington Memorial. And, you know, the thing is, all those answers are correct. Because with the information that you had, you mentally assembled that and came up with the identification as you saw it. And the more information I give you, the more narrow you narrow it down. But the fact is, you know, your brain just takes the information you've got, it assembles it, brings other things together, and mentally assembles those things to create the complete object. We are going to talk about a concept called Gestalt. Gestalt is not the name of a psychologist. It is a German word that basically looks at the entirety of something. It particularly focuses on grouping principles. there are 4 people that are particularly associated in psychology with the approach called Gestalt. Gestalt has 2 parts. One are the people that concentrate on shapes and perception, and then there is the part of therapy that's called Gestalt. The people who are looking at the shapes and grouping and perception, some of the big names there are Wertheimer, Kohler, and Kafka. The therapist that is most associated with Gestalt is named Fritz Perls. Now, with Gestalt, there is a sentence that is totally associated with this approach. And it is the definition of this approach. The sum of the whole is greater than the sum of the individual parts. The sum of the whole is greater than the sum of the individual parts. Now, I'm going to tell you, for years and years, I taught what the book told me to teach, but I don't think I really grasped what the concept truly was. And then one day it hit me like a ton of bricks. And it's like, how could I have ever missed it? The best way that I can illustrate to you the sum of the whole is greater than the sum of the individual parts is by introducing the greatest rock and roll group of all time. Now, before you take me on and say, no, you don't know what you're talking about, I think I can prove my point. The greatest group of all time were the Beatles. Now, why do I say they were the greatest? Well, first of all, they were the first ones to hold down 5 of the top 10 at the same time. They held down 1, 2, 3, 4, and 5 at the same time. They changed the fashion industry. They changed the haircut industry. They affected the cinematic industry. They set records on attendance for concerts. Their music, 50 years later, is still looked at as classic, incredible music. Very, very talented. The music itself changed the musical industry. It changed it worldwide. They had an economic impact on America and, of course, Great Britain. They also affected spirituality across the world. They were the ones that basically openly admitted to taking drugs, and so therefore so many people following them started experimenting with drugs. So that was an aspect that they affected. They sold hundreds and hundreds of millions of records, and even 50 years later they're still selling records like you wouldn't believe. In 1969, 1970, they decided to break up. George Harrison went his way, wrote music, had a production company, made movies, did concerts, recorded records, made millions of dollars. John Lennon went his own way. He wrote a lot of music, recorded some. He was actually assassinated in 1980. Ringo Starr formed a band called the All-Star Band. Had some #1 hits, sold some records, made some millions. Paul McCartney, he is still performing. He has even written Broadway music. I think he's won a Grammy for some of his music that he's written. He's still touring. He's actively writing, actively recording. Very, 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 very rich. But when these four split up, no one person had the impact that they all did together. Even if you took every one of their achievements and tried to see